Hello everyone, this talk is titled Under Stability of Connected Autonomous Vehicle Networks with Commensurate Time Delays. The authors are Isam Al-Darabse, Muhammad Al-Junaidi, and Sue-Ann Campbell. We are from the Department of Applied Mathematics at University of Waterloo and the Department of Mechanical Engineering at Memorial University. Outline of the talk. I will start with the main challenge in connected autonomous vehicles networks, with focusing on communication delay. Then problem formulation and modeling of connected autonomous vehicles network, considering commensurate time delay between the vehicles. And then stability analysis, string stability, simulation results, and the last part is to conclude the paper. So in this slide, we present the main challenge we have in connected autonomous vehicle networks, and this includes false data injection within the communication links, nonlinearities due to human-driven vehicles when they exist in the platoon, unknown disturbances, communication delay in communication links. As we can see in these figures, these challenges will affect the security, safety, and stability. And in this study, we'll focus on communication time delay between the vehicles. In this slide, we'll focus on communication delay. So communication delay limits the accessibility to accurate information between the vehicles. And these informations include distances and velocities. And as we know, communication delay could affect the system dynamics and performance. So in this paper here, we consider increasing in communication delay as distance between vehicles increases. And this could be one of the worst scenarios in V2V communication delays. So as we see in this figure, we considered more delay as distance between vehicles increases. So this paper, we consider n+1 vehicles in a single lane road, and we assume I equal to 0 up to n. The index I equals 0 is the leading vehicle, and n represents the number of the following vehicles. As I mentioned before, we consider communication time delays increase as distance between the vehicle increases, as we can see in this figure. So problem formulation, here we consider the following control system for a curved platoon with commensurate time delay. SI-VI present the states of distance and velocity of vehicle I, and here we consider the following control signals, UI of t, where beta and alpha are control gains, and here zeta ij presents a communication delay between the vehicles. And here we consider the following velocity function, where we have 0 if the distance is less than the h as a stop, the minimum distance we have, and cosine function to present the smooth velocity between h stop and h go, and Vmax if we have h larger than the h go. And also here we present the function of the distance, hij of t. And here is the uniform flow equilibrium that we consider here in this study, that we have SI star equals V star times t minus I H star minus the summation from K0 up to I minus 1 for L of K, which represent the length of the vehicles, and VH star equals the desired velocity V star. So stability analysis, first we present here plant stability. So plant stability is obtained above the flow equilibrium in the presence of commensurate delays, and the objective here is to obtain the maximum admissible delay region such that the cabin system remains stable. So the plant is stable when the leading vehicle moves with a constant speed and perturbations in the states of distances and velocities of following vehicles approach to 0. So the two delays are said to be commensurate if the ratio is rational number, and we use the following equation to represent the commensurate time delays. Zeta ij equals I minus j times epsilon. So in case that we have 4 vehicles, we will have epsilon, 2 epsilon, and 3 epsilon. So in this slide, we present velocity and distance perturbation parameters about the equilibrium to obtain the state space presentation of vehicle I considering the commensurate delays. And here we present the model and its parameters A0, Aij, Bij, psi ij, and gamma, which is alpha plus beta. Then here we obtain the status space model of the platoon with n following vehicles. And here are the parameters of h node and hk. Then we assume for the solution x of t equals c exponential s of t in order to obtain the characteristic equation, which is delta s epsilon determinant of these parameters equals to 0, and we need this equation to obtain the stability exponent at s hat, which represent the maximum real value of stable roots. So the main idea here is to replace the eigenvalues of characteristic equation by generalized eigenvalues of some matrices P and Q. And here we present the matrices P and Q, and please keep in mind that the last element of matrix Q is Hn minus 1. So then we are ready to present the following theorem. So let the rank of Hn minus 1, which is the last element of matrix Q, is R. Assuming we have a stable system without the delay, then we can have different solutions, epsilon I bar, and here we will consider the minimum epsilon IR bar to be the epsilon star, which is proposed here for plant stability. So string stability, so here we study string stability with commensurate time delay. So this concept is essential to avoid amplifying space errors through the traffic flow, and we need to obtain the transfer function that characterizes the dynamics between the velocity. And here we obtain the transfer function Gij of xi, considering the commensurate time delay. And then we can obtain and characterize the dynamics between the vehicles, as we can see in this equation. Vi of xi equals Tij xi times Vj xi. Then to ensure that we have a string stable platoon, we need to ensure that the superior value of the absolute of the transfer function between the leader n I equals 0 and the last vehicle that we have n is less than 1. The t function here is called the link transfer function, which acts as a dynamic weight along the link between vehicles. So here we perform simulation result considering the following constants. So we have n equals 1, h stop 0.1 meter, h go 2.2 meter, alpha 0.8, beta 0.2, v dash h star 0.182, v max 0.25 meter per second, h star 1 meter, gamma 1, size r 0.146, 0.218, 0.267, and 0.303. So consider here 5 vehicles. I equals 0 represent the leader, and n equal 4 represents the number of the following vehicles. Without delay, we have a stable system, so the velocities approach 0. And considering the delay and using the theorem that I presented before, we obtained epsilon star equals 0.197 second. So here we considered 3 values for epsilon 0.12, epsilon 0.19, and epsilon 0.21 second. So it's clear here that we have stable trajectories with epsilon 0.12 and epsilon 0.19. Both of them are less than 0.1976, while we have unstable trajectories with epsilon 0.21 second. And also we can see that we have less oscillation for the case of 0.12 second. So in this slide we show the effects of having commensurate delays on the control gains. So again here we consider 3 values for epsilon, 0.12, 0.19, and 0.21. The stability region is colored by blue and the unstable region is colored by yellow. So it's clear here that the area becomes larger when we have less commensurate time delay. So for epsilon 0.12, we have a larger area compared to epsilon 0.19 and also compared with 0.21 delay. So in this slide, I present a simulation result for string stability with commensurate time delay. So here I considered two cases, 0.12 second and 0.19 second. As I mentioned before, we need to obtain the transfer function that characterizes the dynamics between the leader and the last vehicle, which is vehicle number 4 here, in order to obtain the transfer function t for 0. And we used the following transfer function gijxi in order to obtain transfer function for 0 xi. So here are the results. So we have stability, string stability for the time delay of 0.12, and we don't have string stability for the case of 0.19 second. Conclusions. In this paper, we study stability of connected autonomous vehicle networks under assumption that communication time delays increase as distance between vehicles increases. And we assumed commensurate time delay where the ratio of any two delays is a rational number. And then we carried out plant stability and string stability analysis, and we obtained the maximum range of delay where cabin becomes stable. And we observed that stability region and control gains become smaller as times delay